We know from Newton's second law that a net force applied on an object causes linear acceleration, and that this acceleration is proportional to the force. We also know that the constant of proportionality is the object's mass, which is a measure of the object's inertia, or resistance to change its state of motion. We may wonder if there is a similar relation explaining the causes of rotational motion. That is, if there is a Newton's second law for rotation. To find the answer, let's consider a point mass placed on a rod of negligible mass, which is constrained to rotate around a fixed axis. We will assume that the mass moves only on the horizontal plane. If the mass is changing speed, there will be tangential acceleration, which is related to the force applied on the mass following Newton's second law. We know that the tangential acceleration is equal to the angular acceleration of the mass times the radius, which is the rod's length in this case. Using this, we can find an equation for the angular acceleration of the mass. On the other hand, to make the mass rotate, we need to apply a torque. This torque will be the product of the force, the radius, and the sine of the angle between them. This angle is 1, because the force is tangential to the circle, and thus perpendicular to the radius. Combining both equations, we obtain this relation between the torque and the angular acceleration. The product of the mass and the square of the radius is called the moment of inertia or rotational inertia of the point mass. This is a measure of the object's resistance to rotation. Note that, because it depends on the distance to the axis of rotation, the moment of inertia will change if the rotation axis is changed. This way, we have derived an expression that is mathematically analogous to that of Newton's second law, and that relates the cause of rotation, the torque, and its effect, the angular acceleration, in a similar way as the force and linear acceleration are related. What happens if we are studying the rotation of a collection of particles? In this case, the net torque will be the sum of the torques applied to all the particles. It follows that the moment of inertia of the system will be equal to the sum of moments of inertia for all the particles. We can generalize this idea to all the particles in an extended body. In such a case, it is more practical to express every infinitesimal mass in terms of density and infinitesimal volume. We then consider the perpendicular distance from each one of these volume elements to the axis of rotation. Solving the integral, we will find the moment of inertia of the body. Using this, we can calculate the moment of inertia of any solid body. Here you have some examples for several common shapes.